So first of all, thanks a lot, Guillaume, for the introduction and for all the organizers for making this week possible. Thanks a lot for the invitation. So in these three lectures, I will talk about issues related to probabilistic inference, and more specifically to its correctness, and to try to see what may happen when you try to evaluate probabilistic programs that we could want to care for when we are focused on semantics. So actually, before I talk about probabilistic programming, let's look back at other programming languages and the kind of semantic issues we are probably, most of us are used to, but I just recall to fix the context. If you are, like me, very interested in functional programming, you are used to very nice, strong typing systems. And a motivation to have them is if we did not, then we could write some programs that we could not expect to have a semantics for. So I give just a few very brief examples without introducing too much formalism, because it's not the focus of the lecture. But if we try to give a semantics to languages like ML, OCaml, SML, and so on, then you can start with small-step semantic rules that tell you how to make transitions to evaluate your programs. And I give one here in the top. If you have a condition and you know the condition expression, and you know that the condition is true, then you proceed to evaluate the first sub-expression. And if you did not have strong typing, you could write all sorts of programs that could not evaluate. Evaluation would get stuck. So I give one in the second line. You have some small function application, and by mistake, I just pass an argument that's a float instead of a Boolean. So execution will make a step to inline the arguments of the function to apply it, and then it will not be able to apply anything like the first rule on the very top, which means the program will get stuck. So in order to do that, many years ago, people who are experts in functional programming designed very nice type systems. And I give a few rules in the middle. So you have typically rules to type functions. If you have a function which has type, an expression which has function type to, arrow to prime, you have some argument expression of type to. You can decently expect E0 applied to E1 to evaluate, and it will return something of type to prime. And you can make a bunch of rules like this, which have nice properties and less nice properties. So a nice property is soundness. That is, well-typed programs do not go wrong. The program I wrote towards the top that gets stuck is also going to be thrown away before you even try to run it. So that's very nice, a feature to have. On the other hand, you have incompleteness, which is maybe less nice, which means that you are going to reject some programs statically, even though maybe by chance they could still evaluate to something meaningful, like the one I show toward the bottom. And this issue you find in many kinds of programming languages. You also find in imperative programming languages, especially like C, for instance. If you are interested in writing code in C, you know you have to be very careful with a number of features of the language. If you manipulate pointers, you may have invalid pointers. And if you write through an invalid pointer, story is even worse because actually anything could happen. You could actually have a crash, which is not too bad because you at least nothing worse happens. You could have some memory corruption, something you don't even know of is modified, even maybe your code. And you could even have, by chance, some executions. That's just fine, by chance. And here, too, we have some static verification techniques that can help. So Guillaume mentioned aix-marseille. So this is one among many static analysis tools that try to statically avoid this kind of problems. So now this is out of the scope of probabilistic programming. So what happens when we look at probabilistic programming? Well, as you saw yesterday, evaluation for us is going to be called inference. So the question is, when you do inference, is it always well-defined? Can this result always be computed safely? Will it always return something meaningful? Or are we missing something? Are there cases where we could have something a little bit like these undefined behaviors or crashes or whatever we just talked about in the probabilistic programming context. So in the 3 lectures I will give, I will actually think about this. I will study this in the context of some pretty advanced inference engines. So actually we will also spend quite a bit of time, actually maybe most of the 3 lectures, trying to understand how this inference scheme works. Then we will see that to have a formal view of its semantics takes a bit of effort. So this is what we are going to do during the 2nd lecture I will give on Thursday. And also because we will notice that there are some pitfalls, some cases where this inference engine will have possible issues, we will also look into verification methods for this on Friday. So that's kind of a very high-level outline of the 3 lectures I'm going to give. And today we are really going to try to understand what this kind of inference engine does, and it will really be like more like a series of demos. Okay, so before we talk about this inference engine, which is called SVI, I will explain a bit later. Just to recall, yesterday Christine and Sam and Raphael talked about inference already, so I just recall very briefly some of the inference engines, some of the inference techniques, sorry, that were mentioned. So the very first one that Christine mentioned in the morning was enumeration, which works really well when you have finite support distributions without too many elements in the support. If you have a support that's too big, you cannot enumerate anymore, so you have to do something else. And doing something else could be either sample a bunch of executions and put some weights on each of them to have an idea of where the weight of the distribution lies, or maybe to do some rejection sampling, that is to generate a bunch of executions and hope that those that are more likely to show up actually take more space in the set of executions that you create, which is finite. Okay? So these are just a few of the techniques, and today we are going to look at another one which Christine alluded to yesterday morning, which is called stochastic variational inference. And because stochastic variational inference is actually fairly advanced, we will take most of today's lecture trying to understand what it does. But at high level, what it does is you just have some model, which is essentially the programs that you would like to kind of evaluate if you have this traditional programming view. And this will essentially describe probability distribution, like we saw a random variable like we saw yesterday. So you have some programs that describe some density function over some random variable x, and you would like to have some idea of what the distribution is. And in order to do so, what you are going to do is to provide a bunch of candidate approximations. So you just have a bunch of programs which are hopefully a lot simpler than the one you would like to understand, that you are just going to give to the inference engine and to tell the inference engine just try to find out among all these what is the best approximation you can take. And the way you do usually is you just give this set as a parameterized probabilistic program. So you have a bunch of parameters. Maybe in some very simple example, we have just one example. I will show some in a few minutes. And you will just ask for the inference engine to choose the optimal value of the parameter, or at least the one that it considers optimal. And that will give you, in this family of candidates, one that is hopefully close enough to your initial program, which is going to be called today model. Okay, so essentially we have at that point we have more questions than answers, right? I mean, what does it mean for a model to be as close as possible to another? So we are going to talk about distance in a few days. How to compute this optimal also is really a major question. And if you are interested in modeling, how do you choose this family of candidates? So we are going to try to give at least answers to some of these questions today and on Thursday. Okay, so first of all, let's have a quick introduction into stochastic variational inference. In the second part of today's lecture, I will show, so this will be very brief. It's just really I'm just going to try to give an idea of how the algorithm works. Then after that, I will show an implementation of it. So we have some probabilistic programming languages that you can install. So one is called Pyro that implement that. So I will show this right after, so that the rest of the today's class will just be a long series of examples, which includes some kind of case study that I prepared just for this lecture. So it's not very advanced example, just to show how to get this to work in practice. Okay, so let's get started. So to get started, we will just consider some very basic example of an application of SVI. We will just assume that we are given some data points. We have some just one dimension. Maybe I can just use this. We have some one dimension space of data points, and we have taken a bunch of values which you can think of as measurements. And for each possible value, we count the number of measurements. So we get some kind of histogram style shape here. So we could say, okay, does it look like some distribution over something? And if possible, can we make this, can we view this as an approximation of a well-known distribution? So if I show this, I guess probably you have some idea of what kind of distribution we could use. Unsurprisingly, I will use a normal distribution that Christine talked about yesterday. So question is, can we confirm this looks a little bit like a normal distribution? And if so, can we also try to have an idea of what the mean and deviation of a good approximation of this set of data points would be among all possibilities of normal distributions? Okay. So to begin with, I will just make the problem a little bit simpler. I will first of all focus on the first point, and the second point I will just forget a little bit about standard deviation. I will just assume we fix one, and later on I will get back to the case where we would also like to infer a good standard deviation. So I will first make the problem a little bit simpler. Let's say we fix some deviation. We still have a bunch of normal distributions. So I am showing here a few in this picture. So for each of them, I show the CDF. And I took a few possible values of the mean. And as you see, some are a little bit better fit than others. And if I had to choose among the three, maybe the one in red would be just kind of right. So the question is, can we confirm that and can we infer it? That is, can we have some algorithm that says, yes, this sounds reasonable, and here is the good value of the average, of the mean, of the distribution to approximate your set of data points, and not have to supply it and just look, which here we can do because we have just one dimension in the data set. If we had many, if we had a lot of data, it would really not make sense. Okay, so let's get started with SVI, like a general view of it at least. So we will assume that we have our fixed model, which is essentially this kind of green histogram here. And this is something that we are given. So now let's assume we just try to make a guess at what a possible deviation could be. So we are going to write something that's called a model that is going to first sample some random variables that I call x, which is actually not quite the one that corresponds to the data set here. It is essentially the one that is my guess of a mean of a normal distribution. So I just pick one at random. I have no idea whether it's good or not. And then after I have fixed one, then I can just go through my data set and say, okay, for each of them, is it a good approximation? If I consider this is a sample, is it a reasonable sample? So if you remember the constructions of probabilistic programs that you have seen yesterday, so in fact the first one is really a sampling. That is, I'm just going to actually pick up from some distribution of possible means some value. And then I have a large number of points in green which correspond to observations of samples from the distribution I'm trying to guess. So I'm just going to actually generate a bunch of samples, and for each of them, I'm going to observe, in turn, each of the data points in green. That is, I'm going to observe this one once, this one twice, this one, I don't know, and so on. Okay? So that's essentially what I try to guess. I would like to have a good idea of what x could be. Okay? And how am I going to do that? I'm just going to set up something that is going to be a set of distributions over possible choices of the average that is going to be defined by a family that is parameterized by some value theta, which essentially says what is the most likely average. So it's like a distribution over distribution. Okay? And in this parameter, so once I fix a theta, then what I will do is just pick up some value that is going to be the x provided by this family from a normal distribution of mean theta. Okay? So that's essentially the problem we have now. So if I look at the problem slightly differently, what we have here is we have a large set of models which describe actually conditional probability distributions of x conditioned by all the observation in my data set. And I would like to actually approximate this as closely as possible by some instance of a subset of all the possible probabilistic programs, which is here in purple. Okay, so and you have many values of theta that are possible. For each value, you have one approximant, and we would like to choose one. So first question is, how do we say that one is better than the other? Rather than just say, look, if you see on the picture, you see one is more fitting than the other. We have to formalize this intuition. So this is something that we will do using something that is called KL divergence that we will introduce on Thursday. Today I'm not going to explain what KL divergence is. Just view it as a measure. It's not actually not quite a measure, but as some kind of measurement of how close two distributions are. Okay? So, and if you just add, you equip your space with a definition of such a kind of distance. It's not a distance, but as a kind of distance, then you can rephrase your problem as we have our model which lives somewhere in this very large space of probabilistic programs with many constructions that you can use. And we fix a subset here in purple that contains a bunch of candidates. For each candidate, we have essentially one value of the parameter that describes it. And essentially what we would like to do now is to find one. We just added a notion of distance. It's not a distance, but a notion of close, how closely related two distributions are. Then what our problem becomes is just find the one that is as close as possible, that minimizes this divergence. So next, the question is how to compute that. Well, essentially we are going to turn to optimization methods. So optimization methods use gradient computation to minimize or optimize, minimize or maximize some quantity. So essentially the idea is if you start with any point here, we can ideally compute the divergence between this point and the model we have. Ideally, again, we can compute the gradient at this point of the divergence. Say, okay, if I'm here, should I go down? Should I go right? Should I go left? And essentially, we are just going to make a step like that and iterate a bunch of times. And hopefully, at some point, we'll get to the optimal. Okay? So this is essentially what gradient descent does. So you start with one of these values of theta here, which is essentially the one you pick in the beginning, which is just, can be any guess you like. And after a number of steps, you get to something. Hopefully you get to the optimal. Maybe you don't get quite to the optimal because optimization convergence is not always something you can really hope for in finite time. So at some point you stop. But hopefully you should be fairly close to the point that you try to reach. Now, in this very high-level overview, I made a lot of wishes without actually making them clear. I said, let's assume that we have one value of theta. We can ideally get the divergence between the model Q theta and the one I try to approximate. And another wish I made is we can ideally get the gradient. Of course, in practice, this is not tractable computation. You cannot quite compute this exactly. So in order to get convergence, we have to solve a lot of problems. And essentially the second key idea of SVI is to use some stochastic version of the gradient descent. So essentially we are going to start with a value of theta, and we are going to take a bunch of samples from the distribution that is at this, that is corresponding to Q theta, and we are going to try to approximate the gradient around this point. Actually, the computation to do that is very clever. So I'm going to talk about this in detail on Thursday. I'm not going to detail the computation of the gradient of the gradient estimate. It's actually quite involved notion, so we will talk about this on Thursday. Okay, so I think that's pretty much it for today in terms of generalities about SVI. What we would like to do now is to see how it works. So we are going to demo this a little bit for the hour to come. So in order to demo it, first we need some language that features SVI, so we will actually turn to Pyro. So Pyro is a probabilistic programming language, which is essentially an overlay of Python, so you can actually download it and try it fairly easily on your computer. If you're interested, I can provide instructions for this. So essentially the main features of Pyro are the following. So it uses PyTorch for a lot of things. It uses PyTorch to represent tensors, but also for auto-differentiation, which is very heavily used in the definition of SVI, as we are going to see on Thursday. And it supports many distributions, many engines. You can try many things other than SVI. So it's actually a nice place to play with many inference engines. Okay? Also, it provides some pretty quick evaluation scheme with a JIT embedded. So you can actually turn, when you write your program, you can actually pass some additional options so that hopefully it compiles at runtime some of your code into more efficient code in the backend. Major development that you could also be interested in is NumPyro. So actually there is a kind of next generation Pyro that is going to be, that you can already download, that is based not on PyTorch but on JAX. So it makes a number of things a little bit nicer for, including for autodiff and JIT compilation. So it's something you can also try easily. It's still kind of in beta mode. Okay, so now I will start to show code, and actually the first model I will show, I will run them on my laptop in a minute. The first model I will show is the one that is corresponding to the one I was showing here to give some intuition a few minutes ago. So maybe we can actually just take a minute to kind of leave the slides and go to see the Pyro code. Okay, so let's see. Okay. Yeah, I'm not sure what is happening here. Okay, so I have a bunch of files here. Which one is the one I wanted to show first? So, okay, so this is maybe small. No, maybe not so small. Is it all right? Should I make it bigger?
Actually, this is cut on the side.
Ah, yes, slide, cut on the side. Okay, well, then I think we need to, yeah, full screen is not going to work. Not today. Maybe this is slightly better, and maybe I can make it slightly bigger. So this is not very nice code. It's just something for the sake of the demo. So the very first thing I did is a script in some functional language to just generate this nice tensor out of my LaTeX code, or vice versa. I forgot in which direction I went. So I mean, the only thing you can see, this has the shape of the histogram I was showing a minute ago, and that's the point. Okay. So I just declared this data, and I don't comment on the import at this point. I have just two small functions which are referred to as model, which is the model we try to approximate, and guide. So guide is kind of Pyro's terminology. I'm going to fix it in a moment. Maybe you already saw it on one of my slides. I tend to use the Pyro terminology myself. So guide is essentially the parameterized family of programs. So let's first look at the model here. So the model is going to first sample from distribution mean. So this is the one. So this is, oh, sorry, I wrote these examples in this morning or yesterday, so maybe some of the notations are not making me very happy. Let me check one thing. Okay, never mind. So mean here is what was called X in the slide. So this is essentially the distribution we try to approximate. And here the first line, Pyro sample, is just the sampling statement that you saw yesterday morning in Christine's class. Okay. Then after that, we need what the model does is, so it gets some data, which is essentially going to be this very beautiful table above, and it's going to just go through the data. So this is what this Pyro plate does. And it will actually just iterate something for each dimension, for each element in the data tensor, which is written here as Pyro sample. You might mistakenly think it's again a sampling. Actually, this is an observation. And you see it because you have this additional argument here which says observe is data. So it just says go through this. So the two lines here. I'm not going to explain the plate today. And so the plate and the sample with observe here are just essentially like a big loop that goes through all the points in my data set. For each of these points, what I'm going to do is to draw some value from the normal distribution of mean, the value of mean that was obtained by the first sampling here. And after that, I'm just going to observe that this value should be essentially my data point. And essentially what this will do is it will score the execution accordingly. And essentially we will just, whenever we run the model, we will just go through a bunch of, through these two steps. First, get a value of the mean from some distribution, and then go through all the data points and score the execution. Okay? So that's essentially what the model does. So here is exactly the same model, but with the notation I wanted. So actually the first, as I said, is what I called X in my slides. And the second one is Z. So this is essentially the conditional observation here. So this is the second case where we just have these observations that are supplied with my data point. So I think after the lecture, I will provide you the slides. Here you have essentially the three constructions of Python that we use here that are explained. So you will have this for reference after today's lecture. Okay, so next, when we continue reading the code, so the next thing we see is a guide, which is essentially the Pyro way of naming the parameterized family of candidate distributions. So how is it defined? Well, actually there is a first line that looks maybe a little bit mysterious. Here again, we call some Pyro primitive, which actually declares a parameter. So what this says is I have a parameter that is going to describe all the elements of the family that this function is defining. It's not defining just a function, but a family. And we can see it because of this param line, which just says, okay, I have a parameter that is called G, like guide, mean, because we are trying to guess the mean of the model. And essentially, we just have to give a starting point. So actually, we can take something else if we like. Here, I just took 0, so we will play with that in a moment. And you will see how it runs. Okay? And once the parameter is fixed, so For now, I assume that scale is 1. Like I said, I will postpone a little bit the inference of also a scale for the normal distribution that we are trying to define. And last, it will sample from mean. So note here that the name of the random variable mean in the guide definition is exactly the same as in the model. And this is very important, as we are going to see. And it will do this sample again with normal distribution, but it will now use the G mean definition of the mean. So I try to guess where the peak of the Gaussian is. And I will use as a scale, well, value 1 that I just gave, and it's just a workaround. I will just get rid of this very shortly. Okay? So at this point, I have just defined two things. I have defined one target distribution that I would like to approximate. So if I look at this program and at model here, and view it a random variable. Essentially, it's a random variable with, sorry, it's a distribution with just one random variable called mean. And essentially, when I will look at the guide, it's also going to be a random, a probability distribution with just one random variable, which is mean. So essentially, we have like one instance of the guide for one value of the parameter which is given here. Okay, so now we have seen essentially the definition of both the model and the guide. So for the guide, there is only one new pyro construction, which is this parameter declaration, where you just say what the optimization parameters will be. And now what we still have to look at is how to put all this together, how to make an optimization that will just infer and hopefully optimal value of theta. Well, essentially you have this bit of code in the top, which looks a little bit magical at first, but I will explain line by line. So actually the first two lines are essentially telling Pyro how to actually compute divergence between executions of model and guide, and what optimizer to use. So I'm not going to discuss too much the first two. I mean, this is things we are not going to play with today. We are just going to actually always use this code a bit like this. Then we declare an SVI object, which is the next line. So essentially, to declare an SVI object, you have to give the model and the guide and these additional parameters that I'm not going to discuss too much today. Then a very important line here is to tell Pyro to set essentially some parameter store to empty. So what the parameter store is essentially where it stores the value of the optimization parameters that are declared somewhere in the guide. So it says initially there is no parameter. We just start with fresh dictionary, and then we will be able to start the optimization itself. So we are just going to iterate a number of times. Some very short bit of code here that just makes a step of the SVI object, and it will pass the data that will be run both in the model and the guide. Okay? So let's look at the code. Oops, sorry. So the code is slightly longer. There are a few more lines that I will explain because this will be a little bit useful for us today. So first, whenever I just extended a little bit the body of the loop to display something which is the value of the loss that is computed when you do an SVI step. Actually, SVI step is able to compute some information of how bad our approximation is or how good it becomes. Like in the beginning, it should be bad. After some iteration, it should be better. So every now and then, so every 100 iterations, I will show the number of iteration and also the current value of the loss. So hopefully it should improve during the evaluation. And of course, after we have run the optimizer, we hope to see some result, which was not shown in the slide, so it's shown here. It's just a basic loop that goes through the parameter store, which we initialize to empty before the optimizer starts, and that should, in the end, contain some values that should answer the questions that we have our model. So let's now run this, and hopefully it will become a little bit nicer. Okay, so I will start with the one that just has information about mean. So it runs. I broke models just a few minutes before the lecture, but at least I did not manage to break this one. So essentially what happens here is we see, by default, I set it to do 1,000 iterations, so it starts with loss that are fairly high, and it's hard to have an absolute reading of the loss. It's more like relative. In the beginning, you can see it is around 100, and then it goes down, and actually it seems fairly stable. Sometimes it's a little bit chaotic. We can see it goes a little bit up and down, but it seems to stabilize around the 46 something, whatever. And then in the end, we get something that's very interesting, which is the values in the parameter store, which says that this parameter G min is around 1. And if you remember the data set, I can show it again. So the data set is here. So you can see you have some histogram that's kind of centered into, it seems like the values are, highest values are around 1. So we get an approximation of this mean that's not too bad. Okay, so actually in the code of this version of the optimizer, I took inspiration from some of the examples you can find on the Pyro web page to add a bunch of parameters to play with your engine a little bit. So we are going to do that for a minute. So actually you can change the number of steps. So by default it does 1,000 steps. We can also play with the learning rate, which is how much it moves whenever we compute one iteration and evaluate the gradient. So if I just add parameter LR, so I can make it something very, very small like this. And what you can see is that actually convergence is actually slower. And actually that's a surprise to me. The mean is now becoming bad. So probably it means that we don't move enough. Like we would need many more steps if we take such a small learning rate to actually converge. I could also take high learning rate. I expect it to also not behave too well. So actually it's not so bad. Actually in this case it's better to have bad learning rate than a good one. We get 0.9. The other one was really far from the target. I guess this is just because we need far more iterations if we want to make learning rate small. Let's try to play with that a little bit. So if I just want to take number of steps, maybe I can make it something like this. It will take a bit of time. Yeah, I'm not sure it was a good idea to make this. I put 100,000. I thought it was. So okay, I will add one more. I think you have this JIT option that, was it minus, I think. Yeah, that does go a little bit faster. Well, I don't think it goes faster. It does not look like it goes faster. Well, okay, I'm done. I think it's more interesting. One thing that's more interesting to play with maybe is what happens if we take a bad guess of the starting point. So let's go back to the guide. In the beginning, I started with 0, which is not too far from the target. Let's start from 10. So, and we will stop playing with this for a minute. Okay, so this is what we get. So I think this is more interesting actually. So what you can see is we really made a very bad guess of where our data lies, because we just said, I guess they are basically centered around 10, and I think if you look at the values in my data set, nothing is above 2, so it does not sound like a very good guess. And indeed, what happens in that case is we start with very high loss, and very quickly it goes down quite a bit, and actually the final value is fairly close to what we want here. So I mean, if we just take a starting point that's a little bit farther, it's not making that bad of a difference. So okay, oh yes. Well, sorry. Very difficult to type while standing up. Okay. Yeah, so I started from negative value this time, also a little bit far, and I end up not too far from 1. So again, you get something. Okay, so that's a first example of a model. Maybe it's a good time if you have any question, and then I will show more interesting ones. Yes.
Is the learning rate always fixed here?
Okay, yes, that's a good question. Actually, some of the details I did not talk about too much is the optimizer we take. Actually, this is the adaptive moment one, which does play a little bit with the learning rate. But I did not want to discuss this too much here for intro. Yeah. Okay. So it's, so I forgot exactly the mathematical definition of it, but it's a measure that is given by the step function of SEI when you make one optimization. I guess it's probably something not quite scale divergence because it does not get computed, it's not tractable, but it must be related to what is evaluated in the gradient. It's a good question. I don't know all the details of the internals of SEI in Pyro, which is actually fairly complex code. So sorry for that. Yeah.
Can you test multiple laws at the same time? And you test if it was a normal law?
Yeah.
Can you test if it was
so not in the same time, but we could write several guides and test them all one by one. And yeah, we could do that. It is a dangerous activity, as we are going to discover in a bit less than 1 hour. But we can do that indeed. We can try different laws. Yeah. Okay, so I will take a variation of this model. So what is this? This one. So as I said, it was not very satisfactory to just say, I'm going to assume deviation is 1 and that's it. So I just changed very slightly. Actually, the diff between this file and the previous one is very small. I'm going to show the diff. So this one is okay. What is yeah. Oh yeah, well, diff is I entered the tensor in one, not in the other. But besides this, the diff is just in the guide. So, well, let's forget the line where I played with absurd values of the starting point. Actually, in previously, so the only real difference is the second one here. I previously just let the scale be 1. So I just say, I'm just going to be happy with Gaussians with variance square equal to 1. That's very limiting. Now, if I just change this and say I also want to infer deviation, I just replace this line by another parameter definition with name scale, so it is going to be variance squared, and I can run the optimizer on this as well. So we will do it now. Okay, so this is the one that does both deviation and mean. Okay, so, well, differences are small. We have 2 parameters, and essentially what we get is, again, a value of mean that's close to 1, and scale of the variance is very, very small, which means, actually, I think we can view this as an indication we have something that's fairly, like, how to say, centered Gaussian. Yeah. Okay, good. So this is pretty much all I wanted so this I presented in the code. So these are the parameters of the optimizers, that we could play with. We could play with the number of steps and learning rates, and also activate the JIT. So you will have this for reference. I think this is pretty much all I wanted to show as far as the introduction to Pyro goes. And now I will show a case study. So, okay, well, this is also, I'm sorry, I talked both about the slides and about the example. So many of the things that are shown here are just were just shown on code, and hopefully it was clearer. So the second model, the second guide that I'm talking here is also taking the deviation into account, and as we say, it's just done with the second, with the addition of a second parameter. Okay. So that's pretty much it for basic introduction to SVI. So now let's do some slightly more advanced modeling. If you have any question, we can take a bit of time here. Yeah, please.
In the model function, you had, if I remember correctly, you like sampled the mean, but then when we switched to also learning the standard deviation, the standard deviation doesn't get sampled. So I guess I'm confused what the sample, like the first line of model, what does that do?
Okay, so what the first line of model does is say, let's pick, so it's a very, very good question. I think it will become a bit more clear on Thursday when I will re-dive a little bit more into the internals of SVI. But what we are doing here is we have a data point, which is essentially this tensor we have above, and we don't really know what the shape of it is, so we are just going to pick up to just say, let's make a guess, let's assume it's some kind of normal distribution. And here we just pick one possible value of the center of the normal of the average of the normal distribution. And then after that, what the loop does, like line, I don't have line numbers here, but like the plate and the sample with observation do, they just go through all the data points, sample from a normal distribution with mean the value of G, that is obtained at the first line, and go through and score all the executions one by one. Is it more clear?
Okay, so that line gets replaced by the third line of guide.
Right.
When you're actually running it.
Right, right. So in fact, what it means is, so I'm going to discuss this more on Thursday. Actually, when we look at this code, we could assume that when we are going to run SVI, Pyro will each time sample from the distribution that is normal distribution of average 0, deviation square 1. This is not the case. It just says, I have a model that wants to take some value from some normal distribution. My first guess is that it's going to be drawn from that, but this is just a prior. Okay? Later, during SVI, what Pyro will do is it will not take mean from this distribution, it will take actually mean from the guide, and it will run through this code and see how good a guess it is. And eventually it will modify the guide accordingly at the next step. And after a number of steps, it will come with a parameter of the guide, which makes this sample in the guide a pretty good replacement for this one. That's essentially the best way to see it. Yeah. So thanks for asking. I understand it's quite confusing, and hopefully it becomes a little bit more clear when we look at the algorithm of SVI on Thursday. Okay. Any more questions? Okay, so in the next half an hour time or so, we will do a little bit of a case study. So what the case study is about is to model some energy consumption thing. So actually this is kind of, I would not say a very interesting project, but sometimes I tend to note things, and I tend to try to understand a few of the things going on. So in my house, I have a bunch of appliances. Some of them run when I'm here, some of them run even when I'm away. And I would like to know what is accounting for more energy consumption. And I take time from time to time to note some values, some measurement of energy consumption. This is really bad data, so maybe it's really difficult to make sense out of them, but we will still try to do so. Okay? So essentially, what do we have here? So essentially, we have a bunch of items that run all the time. Like I have a fridge, of course, still running when I'm in Marseille. I have a bunch of monitor systems, like network heating systems that are still not completely off. It's not electric heating, kind of different system, but still there is some electric monitor going on. And when I am there, I'm doing a lot of stuff in addition to the basic usage. I'm, of course, cooking, so I use the oven. I am using computers and lights all day. Sometimes washing machine, very often listening to music. So, of course, I use a lot more electricity when I'm there, okay? So now if I try to see what is basic usage when I'm away, what is usage when I'm here on average, and have some idea of how it is, well, I should take time to note some data. So now, not all of you are from France. Some people know that in France, normally we should have quasi-mandatory smart electricity counter. I don't have that for some reason. So let's not get into the politics of that. But I don't have it. So because of that, all I can do is when I think about it, not so often actually, I just go and pick up one data point. I just take a measurement. I go to the electricity counter and note the date in some spreadsheet and say, okay, today, this is how much I have consumed since the house was built. And essentially, this is very bad data for many reasons. So one reason is the counter is of very low precision. Of course, it's just 1 kilowatt hour, so not very precise. When I take measurements, sometimes I forgot for a couple of weeks. Of course, it's not very good because I don't have intermediate data points. I just know I was away for 5 days, I was here for 9 days, and here is the total. Of course, this does not give very direct data. Also, even if I just take measure every day, maybe one day I will measure in the morning, next day I will measure in the evening, so it's not exactly 1 day. So all this is really bad. So now let's try to make sense out of this, and let's try to use this as an excuse to use SVI. So, okay, here is the data we are starting from, and then after that, I'm just going to make some model that's going to be bad, and maybe another one a little bit better. Hopefully, by 10:30, we have a model that we are a little bit happy with. So what is data like? Well, I just have periods where I just, like between two data points with a number of days, I know how much energy was consumed, and I know how many days I was here, how many days I was away. I just have to look at my agenda, which I still have, so that's thankful. And essentially what we would like to do is to have some idea of what is the average electricity consumption when I'm here, and what is the average when I am away. So that's a very rough goal, but let's try to get there. So, and actually we will do several models from simpler to more complex to get there. So first draft, let's make a bunch of assumptions to have models that are simpler and that we can hopefully run and understand quickly. Let's assume that I just only have points for periods where I am here. And let's assume that I make one measurement every day. So that's, I don't have the ability to do so, but for now, let's assume I have. So in this case, I can just actually use a model and a guide that are very similar to the ones that I have shown before, right? I mean, if we just go back a little bit in the previous slides, essentially what we have is, well, so data points are not just number of occurrences of some value. We just have a bunch of measurements. Each of them is going to be a value in the amount of energy line, and we have essentially some density, and we could try to approximate this also with a Gaussian, okay? So that's what the first model will do. And actually the first model and guide are exactly the same as I have shown before. So that's why I make all these assumptions, because I wanted to kind of reduce the difficulty of going from the data set, which is a lot more complex than just a bunch of just an histogram, to a model and guide. So what I would have here is pretty much the same code as before. So here I have one, so actually I made some typo here, I'm very sorry. So I have a model that just samples some mean of the consumption that is going to go through all the data points, which are essentially daily measures, which I will assume for now that I have. And essentially for each of them, it will observe that a sample from the normal distribution centered around the average consumption is equal to my next data point. Okay, so that's model exactly the same as before. And for the guide, well, we have to guess the two parameters of a Gaussian. So we just have two parameters and one sample with the appropriate parameters. Okay, so actually we can run that immediately. Okay, so I will first show some data. So what do we have here? So I just have, so actually this is just kind of fake-ish data because I don't have daily measurement like I said. I just took my spreadsheet and for each period where I was here all the time, I made some approximation that every day I use the same amount of energy during that period, so I did just a division. So that's why you get these pretty strange looking values here. I'm not proud of it, but that's just going to get us through our first model. And that's going to be a good starting point. Okay, so let's look at the model. So I think it is energy. So this is, oh no, this is daily, okay? Okay, so what we are going to do here is, so you can see, again, the model samples from a normal distribution, some mean, use this as a mean for a normal distribution where it samples some value that is observed versus the data point, and the big difference with before is that data points now actually come from, let me make this a little bit bigger, not too big, and not to the left. So data are just taken from some CSV file, which is the one I have just shown, and essentially everything else in the program is very similar. So we are just going to run this now. So if you are interested, I can comment a little bit on the pre-processing of the data, but I think it's not very interesting. It's just some Python packages and that's it. So, okay, so we just start our model. And what we get now is, again, so I made a guess. Let's see what guess I made. So I took as a starting point 5. I think it's too easy. Let's assume that on average, I don't consume anything as a first guess. Then after a number of iterations, Xavier says, no, I don't consume nothing when I'm here. I still have some energy consumption that's around 5.6 kilowatt hour. So it's kind of a guess. And when I look at the values and try to do some, it really makes sense. So that's actually quite a decent guess. Quite a decent guess, but for a bad model because of the two assumptions that I have shown in the top, that I assume that I was always here and that I take measurements every day. Okay, so now I propose to spend, let's say, about 15 minutes or so trying to get rid of those two assumptions. So what I will do is I will first try to get rid of the second one, and then I will get rid of the first one. So question is how to lift assumption 2. So what are your ideas? Is it easy? Is it difficult? So what I would like to do now is let's show some other, the new data we will consider after we move to option 2. I think it's important to show the data. So I think this should be, yeah. So I'm just considering period where I'm home. So for what I have here is I have some periods with a number of days like 18, 9, and so on. And for each of them, I have one total consumption over the whole period. So how could I try to model this and eventually guess something that is hopefully a little bit better than what we had, or at least not worse, as an estimation of the average daily consumption? Okay, so maybe if there is no idea, we can try to maybe, well, let's look at the data. Maybe it's more fun to look at data than PDF. So if I just look at a period like this one, I was here for 5 days, which means that if I just have some kind of guess of what the average daily consumption is, essentially what I want to do is to say, okay, first day I will draw some value from that distribution. That gives me the consumption of the first days, and I do the same for the second day, third day, fourth day, fifth day. I want to sum this all and to say now I observe that the sum is equal to, well, this number here, which is 26. Okay? And I want to do the same for all the data points. Is it going to work? So, of course, if I ask the question, it means answer is most likely no. So, and I have to take a little bit of time to explain why. And to explain why, then essentially let's assume that I have just a period of 2 days. So I just took one data point after 2 days, and of course, to have a realistic model, I will have to have many more other periods, but let's just focus on one of length 2. Then essentially what I would have is I would like to write a model that is a little bit like this one. First, I take a guess of the daily consumption, okay? Then I take a sample from the first, from the corresponding distribution for the first day, and I do the same for the second day, right? This gives me 2 values, and I would like to say that now I observe that the sum of these 2 values is what? Then I have many problems. First problem I have is that the goal of SVI, like we saw, is to find some distribution that is going to be one instance of the guide that is going to describe distributions over all the set of random variables that are sampled by this. But here, this model, which is, or at least this start of a model, exposes C-min as it should, because this is what I want the guide to optimize for. But also C1 and C2, which I really don't want the guide to care for, and I don't want to write in the guide that I have to make a guess about what I use on the first day and second day. I mean, I just want to have a global average, and this is really not going to be a good start. Okay? So we have to change a little bit our vision. So does anyone have an idea of what we can try to do next? Yeah. Right. Exactly. This is exactly what we want to do. So we have to look a little bit at how to make another distribution that is a little bit more meaningful for my problem, which is exactly the one that you have described, which is how to actually, if you pick a guess of the daily consumption, and now you have a data point which says n days, that much energy consumed. Let's see how to make a guess that corresponds to, a sample from a distribution that corresponds to n samples, to the sum of n samples of the initial distribution. And thankfully, there is a tool for that in probability distribution, which is mixture distributions. So if you take normal distribution, actually you have a way to compute this. If you look in the probability theory book, you can actually see that if you are given 2 normal distributions with average mu0, deviation square 0, and say here, so square sigma 0 square, and same here x1 random variable that is following our normal distribution of average mu1 and square deviation sigma 1 square. So essentially, we can actually define the random variable that is the sum of the 2, and that is essentially going to have as a distribution the normal distribution of average, the sum of the means, and of square deviation, the sum of the square deviation. So that means that if I have just one data point for 2 days, I can actually now make a model that works, which is the one I've written here, that will take a guess of mean, which will also be found in the guide. Then it will compute the mean, which is here, which is mean that values that we sample from the mean guess multiplied by 2 with square variance 2, and we have to observe our data point, which is actually this energy that was measured for 2 days. Oh, yeah, please.
Could you repeat again why the previous method is not ideal?
Why the previous method is not ideal? Actually, there are several reasons for that. The first is what we wanted to do is to say, okay, I have a guess of what the average mean is, and then what I will want to observe is the sum of a number of samples. Now, if I make each of these samples, then it means that my model has one random variable per sample. So each time I do a sample, I have one random variable in my model, and SVI imposes on you that the guide and the model should have the same set of random variables. So this will actually not work ever, because you don't want to have a guide that says I try to infer value of for the first day, for the second day. So that's actually the core of the issue. And the second thing is that what you observe is actually the sum of those two values. So, but once you have done those two samples, then you don't have any sampling anymore to do. So when you write the observed statement, you don't even have a distribution to give, or maybe a direct, but I'm not even sure SVI would do anything with that. Yeah.
For the first point, the two random variables C1 and C2 are observations. So
Oh, yes. This is wrong. This is a typo. Actually, what is an observation is that E1 plus E2 is something. Sorry, Guillaume. Thanks a lot. I mean, if you can take notes for them, I will gladly fix the slide. Yeah, please.
What about pre-processing the data that we have in order to make it normalize?
How so?
So if we have a conception for 5 days, replace it by 5 conceptions of a fifth of this conception.
Okay, so issue is that this induces a bias. That you always assume that when you have a measurement for 5 days, you add some information to the model which says that during the 5 days you use exactly the same amount of energy, which is maybe not something that's true. It could be that on one day I used a lot, next day I did not do much, like one day I wash the laundry machine uses a lot of energy, next day I do nothing, Thursday I cook something for 3 hours in the oven. So that would be kind of wrong. No, it does not. It does not. So model that I am suggesting. So actually, first of all, let's get back to the very first model I have shown before, like the first draft. I have to apologize and say I did exactly what you suggested, which I say now is not actually quite optimal in terms, but I wanted to show a first model. Now, the second model, what it does is something a little bit more clever. So this one actually is not correctly written here, so I'm going to switch to the Python implementation, which hopefully is correct, and then I can explain and answer the question there. So let's. So it is energy, and this one is when I'm at home. Okay, so here is the file. So we have a data set with essentially two, so it's a two-dimension tensor, it's just a spreadsheet. First column is a consumption, second column is number of days. And then the model is here, so it just samples from some normal distribution. So here for concision, I just assume that deviation is 1. So I can leave this assumption later, but because we already talked about this, I simplified things a little bit, so I assume that every day I have one, I have one distribution from which I am going to sample every day, okay? Now, next, when I do the observation, what I do is I take a normal distribution, the average of which is the guess of the daily consumption that is done, is obtained here, multiplied by the number of days. So I am using a mixture normal distribution where I just add n samples, days samples for one data points, and with variance square, which is the sum, 1 plus 1 and days time, so it is days. And the observation is just the total value for the whole period. So in this model, I'm not assuming any balance between the days in a period. I just take them as a whole, and I just say, okay, all I have here is information that the whole, the sum of these values is equal to some amount, without adding assumptions that it should always be the same. So if I were using the previous model, then I don't know, if I had a long period on which, for some reason, I never do laundry, I never cook, and consumption is very low, then I would bias very significantly the whole data set. Is it? You seem not convinced. So.
In the end, what you get as a result is an average per day.
Right. But essentially, I'm taking into account the fact that I don't have information on each specific day. I have just a global information, which is much less informative. Yeah, sorry.
This would be like manufacturing data.
Right.
And feeding to the model. So
right. Right. And manufacturing data is what I did for my first example, but I said it was bad, so I apologize already for it. Yes, sorry.
In the guide, you still have a parameter for the scale. Is that, and that's just like getting them out?
Sorry?
In the guide, you still have a parameter for the scale.
Ah, okay, so good question. So this is actually the scale of the guess. So the guide itself is going to infer two parameters. So it's going to sample MH from a normal distribution. So it just samples one value of, so this is the average. Now, what the guide will give you when you do the inference is the guessed value of the guess and a scale over the guess of the guess. So, and indeed, if I wanted to add deviation, then I would have to add two parameters here, one for the deviation and one for the scale of the guess of the deviation, and I will optimize and get many more values. So this is why I simplified models a little bit here. Yeah. Okay? So I think that I have shown this model for too many minutes without running it, so let's see. So, okay, so, but maybe it's not so clear. Yeah, Guillaume told me that the left part is not good, so. Okay, so what I get now is a new guess of the average, which is here. So on average, every day when I'm home, given these measurements where I have just rough sums over periods of numbers of days, which are often ways too large for this to be very good measurement, I get this average, which is again making sense. Okay, so now let's, I think we are getting closer. Oh.
The other results.
As a previous one. So I think it's not, so actually that's a good question. I think it's not so different. No, this is daily. Yes, this is daily. So yeah, so this is the manufactured data. And well, I mean, I guess if I just play with learning rate and well, no, I'm not going to go through this rabbit hole. I think if I start to play with learning rate and number of iterations, I could have larger differences than what I see here. So I think here, the main advantage we get is maybe the peace of mind of not having done something bad, which we did in the first model. So that's, but I think it's priceless. I like peace of mind. So indeed, not too much difference in the result. It means that in this case, bad model was not so bad. Maybe, I don't know. Yeah. Okay, good. Okay, so let's go back to these two assumptions. So essentially, I have just shown how to lift assumption 2 with mixture model. Now, what do you suggest to do to lift assumption 1, where I have also information? Sorry, no, this is not. It was right. Okay, I'm lost in my. Yeah, here. Okay, so we had those two assumptions we did not really like, so we did manage to get rid of assumption 2. So what should I do to also get rid of assumption 1? So I now want to also have data points. Again, I'm going to show the data, but essentially now it's going to look very much like this table. So I have periods for which I have a total number of days, how many days home, how many days away. The sum of the two is the number of the days, no issue here, and total consumption. Yeah.
So one thing you do that relies on assumptions that are obviously false, but you would introduce a Bernoulli variable.
Mm-hmm.
I'm at home and not at home with parameter as a parameter as well, and then you have 4 parameters, like at least 2 means and 1 or 2 standard deviations.
Right.
And then your model is picking from.
Okay, so that's an idea. I think we are going to do this or something a bit like this next. So, but it's a good suggestion. Which will be yeah. So another thing is what we could do is just say, okay, we have 2 kinds of days. Days where I'm here, days where I'm away. For each of those 2, I have some energy consumption that should be some kind of Gaussian. And we have just seen mixture models. So if we know how to sum 2 Gaussians, we can know how to sum a large number of Gaussians. So maybe we can just integrate this with mixture distributions. Okay? So that's what I suggest first. So if I do this, so we used mixture distributions to account for the fact that I had 1 measurement for a period of n days. Now, next thing I can do is do the same, also use the same mixture distribution for to sum essentially a number of measurements of 2 kinds. Some of them are days where I'm home, some are for days where I'm away. Okay, so let us immediately look at the implementation. I think this is more. Okay, so which one is that? Oh, this is 1. Okay. Okay, so everything becomes a little bit bigger, but it should not be too long to go through. So we have a little bit more processing to do for the data because we have, again, we have lines with 4 numbers. One is total consumption, one is total number of days, one is number of days away, number of days home. What is interesting is in a model. So for the model, what I propose to do is to first have a guess of what the average consumption is when I'm home, another for when I'm away. Then I'm just going to iterate through the data points I have. For one data point, I'm just going to observe the consumption to be a sample from a normal distribution. The mean of is the number of days I spent home times the consumption when I'm home, plus the same when I'm away, okay? And for the number of days, it's a total number of days, I do the sum, whatever, okay? So that's a new model. And I can now look at the guide, which becomes already a little bit more complex because I have 2 Gaussians, so I have to have 2 parameters for each Gaussian. One is the mean that we guess. Another is essentially the scale of the guess. So I'm not going to discuss guide more. I'm just going to look at execution of this. So maybe before that, maybe I can show the data. Okay. So this one is actually the actual, so it's actually the actual spreadsheet I have, which with a bunch of data points. And yeah. And as you can see, measurements are far from regular. So yeah, I'm not very serious about it. I should have one of those smart counters, maybe. Sorry, what is the name of the file? Ah, yes. So this is home or away. Yeah. Okay. Ah, sorry. Okay, so what we get now is we start, so you can see the loss is starting to decrease, and then it stabilizes around the 200 or something. So hopefully this is optimum. So it says that when I'm around, the average that we get is around 5.4. When I'm away, the average we get is around 1.4. Again, looks kind of in line with the data I mean, I did not go through a long process to confirm this. I ran this yesterday or so that was not very thorough job. But anyway. Okay, so now we could change a little bit the model, and I think I'm going to pick up on the idea that you have mentioned a bit earlier, or to actually pick up a similar idea. Maybe we can play with the models after if you want. So essentially what we could try to do is to take more assumptions into account and say, okay, what happens if I'm away? Well, sorry, if I'm away, the consumption I should get should be lower than when I'm here, obviously, because when I'm here, I run more stuff than when I'm away. So let's try to use this assumption differently. I don't think I followed exactly what you said. I followed a variation of that, and I changed the code right in the morning, so it could be that we don't have exactly what we want on the screen. I will run it in a minute, but essentially what we're going to get is a crash. That's quite interesting to investigate. So what I've done here is first I just did a sample to get what is the energy I consume on a given day when I'm here. So that's something I sampled from a normal distribution. And then I said, okay, when I'm away, actually I'm going to use some amount that is between 0 and what I use when I'm here. So I'm just going to use a uniform distribution between 0 and the result of the first draw, okay? So, and then everything else in the model is the same as before. These 5 or 6 lines are exactly the same. I'm not sure, is it exactly what you suggested? Maybe not exactly?
No, because I didn't know you had the information of exactly how many days were.
Okay, yeah, indeed, that. Right. But I think that some of the principle is in here, like we use this assumption and we think we are doing something good, and actually Python is not going to reward us, or Pyro, I would say. So let's run this. So maybe I can actually show the file. So because I did a few more changes, I think, let me check. No, it's okay. Okay, so let's run it. So, okay. So as promised, I get a crash. What we are going to do is to read a little bit of the message of the crash, and that gives us a little bit of insight. So what is happening here, I'm not sure how readable it is. So it just says there is at some point some distribution that is where is it? Mentioned. Uniform, yeah? So we have uniform distribution with bound 0 and 2 something. And at some point, Python complains we get some value that is not in this range. And I don't see where the value, yes, the value is here. So we get minus 0, 20 something. So how come could we get a negative value here? Is something that in order to understand that, we have to actually look again at how SVI works. So essentially what SVI is going to do is to never sample directly from the model. It's going to sample from the guide, and it's going to use the samples of the guide in order to refine later the values of the parameter that we get in the model. Okay, so if we do so, then if we use some normal distribution in the guide, of course, we at some point get some issue that Pyro is not going like we are going to get out of the support of the uniform distribution. So we can actually try to fix the guide. This is what I was playing with this morning, because we can also try to put some uniform distribution with some range in there, but again, we get into trouble really quickly. So I guess we could keep trying to fix this idea, but I think the core of the problems that we have here is that as long as we try to run SVI on our model and guide, essentially we have to account for the fact that the SVI algorithm will assume some kind of relationship between the model and the guide that is very strong. And it's very easy to break this assumption when we try to do something like this, like to get this additional assumption and to draw some some parameter a little bit more smartly with some different distribution. So that's actually something I will stop on because it's 10:30 and also because it's perfect motivation for what is going to follow. So essentially what we have seen today is that actually SVI is a very non-trivial method that takes not only one probabilistic model but a pair and then run some optimization on them. We are going to discuss the inner of SVI on Thursday, so we have to actually do a lot of semantics to understand how to even get approximations and estimations of the gradient of the distance. But also we have to understand what are the assumptions that we make when we look at the theorems of correctness of SVI that actually can lead to issues when they are not satisfied, like what we have seen here is actually a case where we have a theorem. I've not shown it yet, it will be on Thursday. And if I break the assumptions of the theorem, then anything can happen. We have a notion of undefined behavior, a little bit like I mentioned early in the course today, but in the context of inference. So on Friday, I will actually talk about how to do some kind of analysis on the model and guide to actually compute some properties that are going to give us a guarantee that the theorem applies. Okay, so that's all for today. So thank you very much. And